Hello, Pietro, and thank you
Hello,
so much for
Dominic.
the
I know,
invitation.
yes, that having very, very small babies doesn't give so much reason to travel. So at least that is something. Okay, so beautiful. We can see very well your slides, and you can start.
All right. Hello, everyone. My name is Dominique. I'm a lead researcher at Valence Lab, adjunct professor at University of Montreal, and also affiliated to Mila, the Institute of AI in Quebec. Today, I'm going to be talking about my work on graph neural networks, where we will, second, uh, yeah, sorry, give me some second. I think there was autoplay. All right. You see my slides again? Yeah. So today I'm going to be talking about like what are graph, how to build standard graph neural networks, make them expressive, build graph transformer, and finally go through application. But I will try to do that in a very visual way and very summarized. So first, we'll discuss like the autonomy of graphs. We'll go through that very quickly because I think most of the audience are familiar. But a graph is made of nodes and edges. So the nodes are connected by different kind of edges, and these are represented in an adjacency matrix. That is the number of nodes, a matrix sized number of nodes by number of nodes. The matrix is set sparsely with the ones or other kind of numbers denoting the different kind of connection between the different edges. And this is a sparse matrix containing a number of edges, non-zero elements. Each of these, when we want to build neural network, like each of these nodes and edges are represented by vectors, and then we can concatenate these vectors to have some matrix representation of like the node features and the edge features of the matrix. Um, Once we have that, we can start like building neural network. But first, we have to consider like what are the symmetries in graphs. And here we talk mostly about permutation invariance. Permutation invariance means that we can swap like the ID of different nodes with each other without really affecting the graph structure. And this is represented also by swapping the elements in the adjacency matrix. Um, and in reality, like there are a lot of different ways to swap things around, and it doesn't change really the graph. There's just no canonical way of ordering the different nodes. Um, then I will talk about the Laplacian matrix very quickly because it's an element that will come back later in the slides. So the adjacency, the Laplacian is built with these two steps. First, we take the adjacency matrix, and then we sum each of the row into a degree matrix, a diagonal degree matrix. And then we compute the Laplacian matrix by simply taking the degree minus the adjacency. And this has a lot of like cool implications in graph neural networks that also link them back to a lot of work like related to electromagnetism or physics in general. So when we look at a molecule is often represented as a molecular graph. So here, like, is a sketchy, not really realistic compound, but you can see that we can map them directly into a graph. And actually, when you go to the pharmacy to buy a molecule to buy a drug, you're actually buying the graph of that drug. This is how it is represented there. You don't buy the 3D structure because a molecule will exhibit many different 3D structure. What you end up buying is the graph, and this is what we want to learn about. That this is what we want to try to optimize in general when developing different kind of drugs. So each of the atoms can be represented as the nodes of a graph, and the edges can be the bonds of the molecular compound. So usually we'll have a node feature matrix that represent, for example, like the atom type. It can be one hot encoding. Same thing for the different kind of edges that we have in the graph. But we can also like dig into like all the periodic table and add other kind of like features like mass, row, column, and these kind of things. Same thing with the edge features. So once we add more features that have been developed and studied by chemists and physicists over the century, it helps the neural network better generalize and do less overfitting. So we go back to like this idea that one of the key things that we want to do with graph neural networks for molecules is to predict their properties. So we use what we call graph neural network, and I'll talk a lot about them in future slides. But then this graph neural network, in general, like we either have binary classification, which is, for example, like predicting whether a compound is toxic or not toxic, predicting whether a compound will bind or not bind to a given protein. Or we can have a direct regression task, which directly predict to what extent it binds, to what extent it is toxic, to what extent it is soluble. So these are like the two things that we tackle in general. Classification has the advantage that it can work a lot better with like low data settings and imbalanced settings and noisy settings. So if your data is sparse or noisy, classification is often preferred, but when your data is higher quality, you would prefer regression. So how do we build a graph neural network to do molecular property prediction? Like I said before, we need to deal with permutation invariance, but also like the varying number of nodes and neighbors that each of the nodes has. The problem of isotropy or like lack of direction. We don't know which node is left, which node is right, like we do with images or text. And there's a lot of problem with expressivity. And in general, like over the years, like the field has like tackled many of these problems. Like for permutation invariance, they apply an MLP on each node and then pass the features over the edges, and this preserves the permutation. So we don't just like swipe over a kernel, but really like pass each of the features on the edges. For the varying number of nodes, this is also tackled by a kind of aggregation or pooling function that are symmetric. Usually we use statistics like mean, max, or sum aggregation. Then there's the problem of isotropy or lack of direction. In many cases, like it has been ignored. And expressivity has been handled like a lot mathematically, but I will show you like in terms of like applicability, how we can tackle these problems. So this is kind of like the goal of the presentation, like how to have better ways of like tackling these kind of problems and build very expressive graph neural network for molecular representation. So first we'll jump into inside the graph itself. So one of the things that's important is graph neural networks operate at the node level. So if we really want to understand how they work, we need to jump into the node and become the node itself and really see like through the eyes of the node what is happening at each layer. So like I said, there's this aggregation function like mean aggregation that take in like the neighboring features and in general like an MLP that is applied. So this has been like the foundation like of the early graph neural networks, like GCN, for example. But the problem is that no matter the color of the box that you end up having, like in each of these, once you pass up the message and you mix up enough colors, you always end up with a brown color. So this is kind of like a poop aggregator. Whatever food you have at each node, you try to pass, it transforms into poop and goes into the different nodes. This is called like usually over smoothing or over squashing. Um, and has been like studied a lot in the field of graph neural networks. Other architecture, like for example, the sum aggregation, is essentially just you can think of it as a bigger mean aggregation. Although in practice, like there are key differences. For example, the mean aggregation cannot even answer a simple question like how many neighbor does a node have? But with the sum aggregation, we can answer this question. So there's a lot of improved expressivity, and there has been some theorem showing that like if the information is sparse, is sparsely represented at each node. Once you sum them, there are ways that you can preserve the information, but this is like very tricky to learn. And in practice, they also suffer from over smoothing, which is the difficulty of preserving like its information, and over squashing, which is the difficulty of sending information over. Um, Another architecture that has been typically developed like is gating, like GATT, the gated attention network, and the gated GCN. So these, instead of like just averaging everything, they learn they learn an associated weight for each of the different edges and then pass the information. So in that specific case, some of the edges have been set to 0. Some of the edges are still weighted strongly. So that means that we get more message from certain neighbors before aggregating. In practice, without using some of the tricks that I will discuss later, it still ends up like assigning similar weights to all the neighbors in especially in molecular graphs where most of the nodes are carbons. So this is like something that by using other kind of tricks we can help alleviate, and that suffers a lot less of different kind of problems like oversmoothing and oversquashing. But they can still happen depending on the kind of data that we have. So if we go back to the graph representation, like one of the things that have really pushed the field forward in the past years has been like the attention is all you need paper, that's showing that like attention is really like all we need to learn any kind of information, and has been applied in LLMs, computer vision, and such. But to apply them in graphs, it's a lot more complicated. Um, and essentially, like because we don't have a canonical way of ordering the nodes, like if we just like apply a naively transformer over there, it's kind of like shuffling all the nodes around and not really like learning about the actual structure. So I will explain in more details like how to handle that. But if we are able to define, for example, directions in the graph, like left to right and up and down, and assigning like these kind of axes to give a position, then we can more easily use a transformer. And if we're able also to bias the attention to say, let's say like, let's add an edge weight to the nodes that are actually really connected in the graph so that the network can learn to give them more weight. So I will kind of discuss these topics in more details now. Um, so first, like I want to go back to like this problem of expressivity, then talk about positional encoding, structural encoding, and relative positions as well. So for the problem of like expressivity, we'll often hear about a test called the Weiss-Feiler-Lemon test. I will not explain in detail what that is, but more like intuitively what happens and why a network, graph neural network, have difficulty with expressivity to begin with. So let's take these two graphs. So these two graphs, I think most of the audience will agree that these two graphs are different. But if we go like inside the nodes, like I told you already, like if we want to see how a graph neural network works, we need to go to the node level. Does graph neural network operate at the node level? If we go at the node level and we start walking around, we can see that we can always like find a path that is always like connected to the same number of neighbors in each cases. And this is the problem because then once you are at the node level, there's no way of differentiating between those two graphs if you can only see your direct neighbors and no other kind of information. So you end up thinking that these graphs are the same. But of course, that's not right. And especially in the case of molecules, like although like these are not drug-like molecules, like they could definitely be molecules, and not being able to differentiate between these would be very problematic. So things that we cannot see without having position, direction, or at least a knowledge of like larger neighborhoods than just direct neighbors. So how do we do that? Well, one thing is like first finding higher order features. For example, like one simple thing is like finding different kind of motifs, like predefined motifs that we know that we want to find, like squares and triangles, and assign these as node features to the node or edge features to the edges to help bias the network a bit better. And another idea is also to use random walks and the probability of a random walk coming back to itself. Here we can see, for example, like in the graph on top, you can see in the graph on top that the probability of a random walk coming back to itself after 3 steps is 0. But in the one below, it's kind of a high probability. And if we do it, the probability with 4 steps, then we see different patterns. So this kind of like probability of random walks coming back to itself, is very important in helping identify graphs. So we can build graphs that are more expressive. Another idea, like I told you a bit about the Laplacian, well, if we can take the eigenvector of the Laplacian matrix, it can help us give, with sign ambiguity, what are the direction of like longest length and second longest length of the graph. And if we apply these here, we can really see like the longest eigenvector and the second longest eigenvector. And these are actually analogous to the sine and cosine positional encoding that are typically used in transformers. So they're very natural ways of encoding positions. And we've shown in like the directional graph network paper that we published that like on different kind of graphs, like these eigenvectors make a lot of like um, intuitive sense to be used as positional encoding. This was the first work that showed like that graph neural network can generalize convolutional neural network when we have the right kind of set of features. So another thing with the graph transformers is that even if we have positional encoding, one of the problems is that like with full connectivity, we destroy the inductive bias of the graph and we have to learn it from data. But most graph neural network data don't have enough data to them to actually learn this bias. So and eigenvectors can also be like quite noisy and hard to understand from a network. So one thing is like to add a bias term. So that bias term could essentially say like when there's a real edge, I want to have more weights associated to these connection than the full connectivity of the graph. And by doing that, it also allows us to it allowed us to build like the first the first graph transformer with actual good results with our spectral attention network paper, and we followed up after that with a lot like of other paper showing more expressivity. Now I'll talk a bit about pre-training also. So now that we have graph transformers, we want to be able to pre-train large graph neural networks to be used in other tasks. So one thing that we did is gather a lot of like biological assay, chemistry assay, and quantum mechanics simulation, and also like some self-supervision algorithm. Although like in our work we ignored that one for the moment. And we wanted to learn like multi-level multitasking. So we built a graph neural network that operated like with many MLP heads to predict all these different properties by using a pooling layer to regress over graph level representation and skipping the pooling layer to directly like learn a node level representation. For example, like the electronegativity, not electronegativity, but electric charge, partial charges of any atom after doing a quantum mechanics simulation. And we also like build a library to allow edge representation, node pair representation, although we haven't used them really for the pre-training. And before the graph neural network, we also had built like an encoder manager to build different kind of positional encoding. I talked a bit about these, random walks, eigenvectors. There's pseudo inverse, for example, distances. And then we used a sort of way to project each of these into different kind of edge representation, graph level representation, node level representation, to build an expressive representation of the graphs, the nodes, and the edges to be able to train the network. And inside the GNN, what was happening is kind of like a hybrid message passing and transformer. So we found that this was the best architecture because the amount of data was not sufficient for transformer to be the best. But in reality, like when doing ablations, either message passing transformer or hybrid perform roughly in the same range, with the hybrid having a slight advantage. So we had like defined a different kind of way to pull graph level representation at each layer. I won't have time to go into the details, but we were able like to build these kind of layers such that they could pass information back and forth between nodes and graph level information, and it doesn't get lost and over smoothed around. So this is what happened. And then at fine tuning time, we just dropped all the layers that we didn't need, and we started to do like fine tuning on a new task while freezing the rest of the network. And we showed that this was very efficient and could be scaled quite a lot. So here we had like, for example, the average performance on the TDC benchmark, the best baseline, and all-time record best if we take the best across every kind of architecture that was submitted there. And what we saw with our work on MultGPS, by scaling the pre-training, we were able to reach the performance of like the all-time record best. And especially by using our proprietary data rather than just public data, we were able to beat the all-time record best, meaning that MultGPS became the default de facto model that was used across recursion and across all the acquisition of recursion for like any kind of molecular property prediction, until except of course like binding affinity, where specialized models could perform better. Yeah, so the problem with that kind of work is that we don't encode the context, like a natural language context, protein context, or cellular context. So the kind of future work and a lot of things that I'm working on, and unfortunately won't have time to talk today, is about how to leverage multimodality. I won't have time to go through that these next slides. So that will be all for today's presentation. Thank you everyone for listening. If you have any question, like don't hesitate to ask. I'd be happy to answer.
Hello, Dominique.
Hello, Pietro.
Okay, you here. No, I was just commenting that your students at Mila will be delighted, enthusiastic of the kind of cartoons that you are using, probably also for lecturing. Any questions? Questions? Okay, from Kellings here. Yes, I think, I don't know if I can, okay, but I can give you this, so that is much.
Yeah, very interesting talk. I have a question about, you have the, multi-different way of doing the position encoding. Do you think that in the graph sense, is there any like a way to say, mathematical rigorous way to say that the certain position encoding is more, reasonable? Like in the loop, you have the inner product will equal to certain distance relation. So in the graph sense, do you think there are some related, judgment or metric to say that?
So there are definitely like some positional encoding that are more expressive mathematically than others. For example, like if you take just like the diagonal of the random walk, which is something that we use a lot, it's definitely less expressive than eigenvector of the Laplacian, or than the full like 2D distance matrix, because it can only work up to like WL3, which is like the standard test that has been used. The problem with this is like the difference here is that this is still the positional encoding that we found worked the best in our cases, because it helped understand the local structure better. While the full distance matrices or eigenvector were more like about the global shape, global position. So in the end, like being more expressive theoretically does not translate necessarily to being easier to use from the neural network point of view. So I would say like there's a very limited way of actually understanding the expressivity of each. Like most of the work that I have seen use the WL test. It's very limited. It doesn't translate necessarily to performance. So you have to use something that works well with your data. In terms of like molecular data, substructure understanding is very, very important. More so than like global structure understanding, especially when you work in small chemical spaces. So that's why that kind of like less expressive but more local positional encoding work best. Does that answer your question?
Well, one small question. Just the model of molecules and graphs. They say that the graphs is a model for molecules, but graphs implies a one-to-one interaction, while if you have even two atoms engaging two orbitals that are overlapping, There are also low-range forces like electrostatic, van der Waals, and there is even, I remember that to have studied something called Casimir effect, that is a quantum long-range interaction. So it's V is a model, but has some limitations.
Yeah, exactly. So the graphs is like the model of covalent bonds between compounds, or at least like the kind of graph that I presented here. Although it's like limited in like what it can understand, it's how a chemist define the molecular structure that they're building. So it's like directly the representation of like what they build and what they end up selling, what the pharma company end up selling. So it's still a good representation. Uh, but if we want to learn like about binding affinity, for example, or like a more specialized tasks of compound interaction, then we're better away with like 3D systems where like atoms can learn different kind of interaction, like van der Waals or non-covalent bond or hydrogen bond and these kind of things.
Okay, thank you very much. So,
thank you again for the invitation, Pietro.
Hope to see you soon in England. So, next speaker, Asim Munawar. So we ask Asim to try to share the screen. I think we are still seeing Dominique. I don't know if